Welcome to the discussion of design and analysis of algorithms. Specifically, we will talk of graph algorithms. We have been talking of graph algorithms. We have seen how to represent a graph, and also we have seen two specific graph traversal algorithm. One is breadth first search and another is depth first search. So today we will look into a particular application of depth first search called topological sorting. So what is it? Let's understand what is topological sort. So you have a set of tasks, let's say, okay, and a set of dependencies within those tasks. Okay, so there is a precedence constraints of the form saying that task A must be done before task B. For example, the way we wear our clothes, okay, so we will wear the the vest before we put on our shirt. After we put on our shirt, it's winter, maybe we will put on sweater. If you are in a very colder place, on top of that you will put up a jacket. Okay, so there is a sequence in which it has to be done. There are tasks, okay, so task A, B, C, D, but there is a dependency between these tasks. Okay, so what is topological sort? It is nothing but an ordering of the tasks that conform with the given dependencies. You are given bunch of tasks, you are given how they depend upon each other. Now you have to sort them or order them in order of their dependencies. Okay, that means if A is dependent, means A must be done before task B, then A must come first, then task B. Okay, so the goal is to find a topological sort of the tasks or decide that there is no such ordering. Okay, and the underlying assumption here is that we represent this problem as a graph problem, and in this graph problem we do not have any cyclic dependencies. That means A depends on B, B depends on C, C depends on A. Okay, so that's what we will assume for the time being. And let's say what is the application of it? Typical application is like in scheduling. When you in scheduling you have task graphs in distributed systems. Usually we first need to sort the tasks topologically and then assign them to resources. Okay, so what happens is you got bunch of tasks and there are dependencies between those tasks. Okay, now you are given resources. For example, let's say you have 3 processors or 4 processors on which you want to schedule all your tasks, but those tasks have to run in a particular order. Okay, because there are dependencies between them. Okay, if task A is dependent on task B, so task B needs to finish first, followed by task A. Okay, so you have to be you cannot arbitrarily assign the task to any processor. Okay, so we first need to sort the tasks topologically and then assign them to resources. Now doing the most efficient scheduling is a very extremely difficult problem, what we call as an NP complete problem, which you will understand towards the later end of the course, that what does this word NP complete problem means. For the time being, you can assume that it means a problem which is not solvable in polynomial time on our regular computer. Okay, or another application is when you have dependencies within the modules or libraries. So how do you order them during compilation? Okay, so let's put this entire problem of topological sorting in terms of the languages of graph. So what is it? We have a directed graph G where you have V as the set of vertices of the graph G and E are the set of edges. Okay, where the edge UV means that task Q must be done before task V. So you got different tasks, you got their dependencies, so you make a graph by doing the following. Corresponding to each of those tasks you will make a node, and then you will say, oh, if a task A has to be done before task B, then I will put an edge between node A and node V. Okay, fine. So you will get a graph, and in fact you will get a directed graph. So an ordering of vertices 1 to V you want to look into such that for every edge uv, u appears before v in the ordering. So you want to finally get an ordering of your vertices such that for every edge uv, remember what is uv, edge uv? U has to finish first, followed by v. Okay, there is a dependency. U should be done first, followed by b. Okay, so an ordering of vertices 1 to v such that for every edge uv, u appears before v in the order. And such an ordering is called a topological sort of the graph G. Okay. So first note that there can be multiple topological sorts of G. Okay. You may get different ordering starting from where you start. Okay. Fine. So we will see. So let's look into the algorithm for topological sort, and the algorithm is very simple. It is entirely dependent upon your depth first search. So if you have understood depth first search, you will be able to follow this algorithm. So in topological sort, G, its parameter is the graph G. Okay. What you do, you call depth first search on this graph G. Now remember, when you do depth first search, you start with a particular node. Okay. And that's the root node of your depth first search tree. And what you do, you start going deep into your graph. Okay. So from the very starting node, you go to its neighbor, and its unvisited neighbor, and then its unvisited neighbor, and so on as far as you can go. Every time you go to a new neighbor, which is colored white, if you recall, you will give a discovery time, that when it got discovered. Okay, and once you visit it, you will mark it as gray, and then you will go to its neighbor. When all of its neighbors have been explored, you will mark it black. Okay, fine, and you give a finish time to it. So call depth first search on this graph G to compute finishing times fv for each vertex v. Okay, so if you recall, in depth first search we assign two things, a discovery time and a finish time. Okay, so you compute the finishing times for each vertex v. As each vertex is finished, insert it onto the front of a linked list. So every time you finish a vertex, you put it in the front of a linked list. And finally, you return this linked list of vertices. Okay. And claim is that the result is just a list of vertices in order of decreasing finish times. Okay. So you said, if you notice carefully, okay, what you will get is the result is nothing but a linked list. The node which you have last inserted, okay, is having a larger finish time than all the nodes which are already there in the list. Okay, fine. That's what this is saying, that note that the result is just a list of vertices in order of decreasing finish time. Okay, fine. That means the first node is having the highest finish time. Okay, followed by the next node and so on. So now we will look into the depth first tree is depth first search tree little bit closely. Okay, so if you recall, let's look into an edge uv of this graph G, okay, on which you have run the depth first search algorithm. Okay, so if you look into the edges of the graph, you can classify these edges into the following categories. One, you have a tree edge. You call an edge a tree edge if and only if u discovers v during the depth first search. That means parent of v is nothing but u. Okay, so you visited u at some point, and then from u you went to v. If that happened, then u was discovered. So u discovered v. Okay, so parent of v is nothing but u. Okay, in the depth first search tree. So that's called a tree edge. If uv is not a tree edge, so there are edges in the graph, not all of them are tree edges. So if you look at them, some of these edges are called forward edges. When do we call them forward edges? If and only if u is an ancestor of v in the depth first search tree. Okay, so if in my depth first search tree, if there is an edge from where u is an ancestor of a node v, there is an edge between them, then that particular edge of the graph is called a forward edge. Similarly, we have a back edge if and only if u is a descendant of v. Okay, so if v is a, somewhere ancestor, u is a descendant, and you have an edge uv, then that's called a back edge. Okay, and what is a cross edge? Cross edge is if and only if u is neither an ancestor nor a descendant of v. Okay, so we can understand using certain examples. So let's look at this example where we are having, let's say in the depth first search, you started with A. So, A was discovered, followed by B. So from A, you went to B, and then from B, you went to C. Okay. And then what you did, let's say, if you notice that, okay, in my original graph, there is an edge. So these edges which we are drawing in green, these edges are part of my depth first search tree. So we started with A. Okay, A was white. We said, okay, let's look at its unvisited neighbor. So B is an unvisited neighbor, it's white. So we said, okay, we will go to there. That means we added this edge between A and B in our depth first search tree, which means that this edge is a tree edge. Okay, so greens are the tree edges. So from B, when we went to C. Okay, from C, let's say we do not have anywhere else to go, because from C there is an edge going back to A, but A has already been visited. So it's not an unvisited neighbor. So we don't go, visit any of its neighbors. So we stop there. But this edge which is there in the graph, okay, this particular edge which is there in the graph is now called as a back edge. Why? Why is it a back edge? Because it is pointing from descendant to the ancestor. Okay, fine. If this is u, this is v. Okay, v is an ancestor of u. Okay, fine. Okay, so that's a back edge. So you can have a back edge between C and B. Also, if I have a back edge in C and between C and B in my original graph, then also I cannot visit it. Okay, because B has already been visited. Then let's say we have a forward edge. In the original graph, there is an edge between A to C. When we started with A, we decided in our depth first search tree that we will go to its neighbor. So A has in this case two neighbors, B and C. And then we said that, okay, let's go to B. Okay, so we decided to go to B, and from B to C. Okay, in that case, once we have made the depth first search tree, we see that there is a forward edge from A to C. Okay, fine. So that's called a forward edge. And let's say we have an edge between, let's call this as C prime, okay, and B. In my graph, I can have an edge like that. Okay, so these will be called as cross edges. Okay, so I hope what is the classification, the edge classification depends on the particular depth first search tree. Okay, how you are traversing, remember there is depth first search tree. When you are doing, there is not always a unique solution. Okay, so you may have different ways of doing it. Okay, so the edge classification will depend upon that particular depth first search tree. Okay, so just have a look. Okay, I got this graph ABC. Fine. Now in this graph ABC, first I said that, okay, we will start with A, and then we will go to its unvisited neighbor. So we went to B, and then from B we will go to its unvisited neighbor C, and then we saw that, okay, there are no other unvisited neighbors of C, so C is done. You assign a finish time to C. Go back to B. There are no unvisited neighbors of B, so you go back to A, and there are no unvisited neighbors of A, so A is done. But notice that in my graph, I have an edge between A and C. So this becomes a forward edge. Okay. So this is one depth first tree where you got between A to B to C. Now, you could have traversed the same graph in a depth first search tree, manner in a different way. For example, you said, okay, let's go to A. Since from A I have an edge to C, C is also an unvisited neighbor, B is also an unvisited neighbor in the very beginning. I start with A. So I said, okay, let's choose the neighbor C. So from A we go to C. From C, there are no other neighbors of C. So we say that, okay, we are done with C, go back to A. And then go to an unvisited neighbor of A. So B happens to be an unvisited neighbor of A. So from A, we go back to B. From B, we see that, okay, is there an unvisited neighbor of B? There is none. So we go back to A and we are done because A has no more unvisited neighbors. Now notice that you got a depth first search tree this time as A, B and C. That's your depth first search tree. And you got this edge in your original graph, which is a cross edge, because it is running between two nodes which are neither ancestor or descendant of each other. Okay, so you got a edge like that. These are called cross edges. Fine. So what edge classification you will do depends upon how you have traversed your graph during the first search tree. So coming back to the topological sort, what you do, you call depth first search tree or depth first search on this graph to compute finish times FV for each vertex V. As each vertex is finished, insert it into the front of a linked list and finally return the linked list of vertices. So let's do an example. So here is an example. You got a graph, a directed graph. Okay, in fact, this is all for directed acyclic graph. In short, we call it as DAG, directed acyclic graphs. Okay, so let's say we start with the node. Okay, in the very beginning in our depth first search tree, all the nodes are white. Their discovery time and finish times are set to infinity, and we just start with unit time 1. Okay, so in the first instance, we will call depth first search tree on this graph to compute the finish times FB. So let's say we start from this vertex C. Fine. We start with this vertex C, so we'll make it gray. Discovery time is 1. And then we say, okay, fine, next time step, go to its one of the neighbors which is still unvisited. So we decided that we will go from C to D. So we go to D. Okay. When we go to D, we discover D in the time step 2. So the discovery time of D is 2. Okay. So the discovery time is 2 for D. Then from D, we say that, okay, we will go to its unvisited neighbor. Now notice that D has also been colored as gray. That means it has been visited. So from D, we decide that, okay, let's go deep. Let's go to its unvisited neighbor. So the only unvisited neighbor of D is F. Right? Okay. So we say that, okay, let's go to F. So your timestamp, discovery timestamp of F is 3. Okay, fine. F has been marked as gray. Also notice the green edges, which are the depth first tree edges, which we are putting in. Okay. Then comes the next time step and we say that, okay, from F, can we go to something else? But it so happens from F, we cannot go anywhere. So we say that, okay, F is done. We do not have any unvisited neighbor of F. So we mark F as black and we say that okay, the finish time of f is 4. Okay, fine. And then we increment the test time. Okay, so you go back to D, fine, and then okay, once you finish f, one thing you need to do is you will put that particular node into the front of a linked list. So you put f in the front of a linked list. Okay, so from f you say that okay, let's go back to D and try to find an undiscovered neighbor of D. Well, there are none. Okay, so you say that okay, then we are done here, and at time equal to 5 we are finished with vertex D. Okay, and you mark that as black. Put D into the front of your linked list. So D has been marked black. Okay, and D, that node D, is inserted in the front of this linked list. From D, the call goes back to C now. So say we go back to C and try to see that okay, if there is, so we first go back to C at time is equal to 6, and then we say that okay, is there a neighbor of C which is unvisited? And it so happens that yes, E is a neighbor of C which is still unvisited. So we discover E. So the discovery time of E is 6. We increment our timestamp. Okay, our time step, it becomes 7, and we say that okay, is there a neighbor of E which we have not visited? And it so happens that there are none. So the finish time of E is done, will be now 7. Okay, now notice that from E, if you look into this edge going to D, that's a cross edge, right? Because between C to D you got a tree edge, from D to F you got a tree edge, from C to E you got a tree edge. Now between E to D you have an edge in the original graph, but this edge is classified as a cross edge because D and E are not ancestor or descendant of each other. Okay, so then your E is done. So you give the finish time to E, put it in the front of your linked list, and then go back to C. Now notice that once you have gone back to C, you increment your timestamp to 8. Is there a neighbor of C which is unvisited? Well, at this juncture there are none. So your C is also done. So put C in the front of your linked list and assign it a final value or finish time. So F becomes your 8. Okay, so note, if there was an edge between C and F, let's say there was an edge between C and F, in that case this will be, that particular edge would have been classified as a forward edge. Okay, had there been an edge between C and F in the original graph, then you will classify that as a forward edge because there is an ancestor descendant relationship between C and F. Okay, C is an ancestor of F. Okay, so if there is an edge like this, then that will be classified as a forward edge. If there is an edge between F and C, that will be classified as a back edge. Okay, so now once you're done with C, you look into, is there any unvisited neighbor in your is there an unvisited node in the graph, and A happens to be there. So you will call depth first search again on vertex A. So you will say discovery time of A is 9 and say okay, from there let's increment our discovery time and then see whether we can visit any neighbor. A's neighbor is B, which is unvisited, so we go to B. Okay, we can go to C, but notice that C has been already processed. Okay, C has been already discovered. So the edge between A and C will be classified as a cross edge. Okay, because A and C are not are having any ancestor descendant relationship. Then we discover B. So we give the next discovery time to B, which is 10. If you look into any unvisited neighbor of B, there are none, so B is also done. Okay, so now it's time to give finish time to B and put it in the front of the linked list. Okay, so you mark it black, give it the finish time 11, put it in the front of the linked list and go back to A. Now A is also done, so you will just give it the finish time, which is 12, and then you will mark it as black and put it in the front of the linked list. Okay, so you got this ordering A, B, C, E, D, F. Okay, so we have the final result, which is essentially the linked list of vertices, and this is what topological sort will return. Okay, and if you notice, the linked list is sorted in decreasing order of finish time. So if you notice, what is the finish time of node A? It is 12. What is the finish time of node B? It is 11. What is the finish time of node C? It is 8. What is the finish time of node E? It is 7. What is the finish time of node D? It is 5. What is the finish time of node F? It is 4. So you got a decreasing order of finish times. Okay, that's your output. So the linked list is sorted in decreasing order of finish times. Okay, you can work with, start with another vertex. Let's say you start with A in the very beginning rather than C, and you will get a totally different kind of depth first search tree. Okay, which can happen. Okay, so if you redraw the graph so that all vertices are in a line ordered by a valid topological sort, then all edges point from left to right. So if you just redraw this graph so that all vertices are in a line, okay, so you will put A, B, C, D, E, okay, A, B, C, E, D, F. Okay, so if you redraw the graph so that all vertices are in a line ordered by a valid topological sort, then all edges point from left. So, if you now notice, between A and B there is an edge. Okay, between A and C there is an edge. All are going from left to right. Okay, between A to B there is an edge. Between A to C there is an edge. Between B to D there is an edge. That's also going from left to right. Between C to D there is an edge. That's also going from left to right. Between C to E there is an edge. That's also going from left to right. There is an edge between E to D. There is an edge between D to F. There is an edge between C to D. We have already put in. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. Some one edge we are missing. Between E to F. So all the edges of the graph are from left to right if we put our vertices in the topological sort order. Okay, that's what it is saying. So what is the running time of the topological sort? It's nothing but theta of n plus m, where n is equal to v and m is equal to e, where n is the number of vertices and m is the number of edges. How we get that? We know what is the depth first search time. It is theta of n plus m time in the worst case, and inserting into the front of linked list, every time what you are doing, you are putting it, whatever is the vertex which is getting finished, you put it in the front of a linked list, which takes constant amount of time. So total time becomes theta of n plus m. So the depth first search takes theta of n plus m, which leads to the running time of topological sort as theta of n plus m. So let's now look into the proof of correctness. Okay, so the theorem says that topological sort G produces a topological sort of a directed acyclic graph, capital G. Okay, so the topological sort, this is the routine we are talking of, algorithm does a depth first search on the directed acyclic graph G, and it lists the node of G in the order of decreasing finish times. That's the claim. Okay, but we must show that this list satisfies the topological sort property namely that for every edge uv of g, u appears before v in the list. Okay, so what it is saying, the topological sort routine which we have given, okay, does a depth first search on your graph G, and what it does is it lists the nodes of G in the order of decreasing finish time. Okay, that's how it keeps on putting into the front of the linked list. What we must show that this list, which is the given output, satisfies the topological sort property, right? Because we want at the end a topological sort, which is that for every edge uv of g, if I look into an edge uv of g, u must appear before v in the list. Okay, in my final list, u must appear before v. That means the finish time of u is larger than v in the list. Okay, so the claim is for every edge uv of g, finish time of u is greater than finish time of v, or other way around, finish time of v is less than finish time of u in depth first search. Okay, so let's see how do we prove that. So claim is for every edge uv of this graph G, fb is less than fu in this DFS. So the depth first search classifies uv as a tree edge. Fine. So the depth first search, if you recall, classifies every edge as a tree edge, forward edge, back edge, or a cross edge. Okay. So here the depth first search classifies uv as tree edge, or as a forward edge, or as a cross edge, but never as a back edge. Why? Because the assumption here is the graph is not having cycles. It's a DAG, directed acyclic graph. That means it doesn't have a cycle. Okay, because having cycle means there is a cyclic dependency in this graph, right? But in the very beginning I said assumption here is that there are no cyclic dependencies. It's not like task A is dependent on task B is dependent on task C, and task C is dependent on task A. Cannot happen. Okay, such cyclic dependencies are excluded. Okay, fine. So essentially, which means that in my graph I will never have a back edge, right? Okay, so now first, if uv is a tree edge or a forward edge, so it may be that uv is a tree edge or a forward edge. So I have from u to v either a tree edge, that means u must be parent of v. Okay, or I might have u and v where it's a forward edge. That means from u I went to some other edge and so on. Okay, from there I went to something else and came to v, but there is a forward edge from u to v. So in either case, if uv is a tree edge or forward edge, it means v is a descendant of u, which means that finish time of v must be less than finish time of u, because this is descendant. Okay, if this is descendant, you will try to go to its neighbors as much deeper as possible. Let's say it doesn't have neighbor, then you will mark it out as black and say, okay, this is done, and assign it as a finish time. And then you will go back, you will trace back to its parents and see that whether their neighbors, unvisited neighbors, have been all visited or not. If they are done, then they will be marked as black. So you keep on going back to ancestor and ancestor. So finish time of v must be less than finish time of u. Okay. What if uv is a cross edge? Okay, so let's see what happens if uv is a cross edge. That means I have some portion like this, and then there is another node and there is a cross edge. Okay, fine, and that happens to be u and this happens to be. So as uv is a cross edge, by definition neither u is a descendant of v nor v is a descendant of u. uv doesn't have by definition any ancestor descendant relationship. So then I can either claim that, okay, discovery time of u must be less than finish time of u, must be less than discovery time of v must be less than finish time of v. Either this will happen, or the other possibility is that discovery time of v is less than finish time of v. See, this part is always true. Okay, fine. Now, since u and v are not descendant, either one of these relation will be true, that either u is visited first or v is visited first, one of them. So discovery time of u must be strictly less than discovery time of v. If u is visited first, then it must have been finished, and then only you can go to v. Okay, fine, because u and v are not having any ancestor descendant relationship. Okay, so du is less than fu is less than dv is less than fv, the finish time of v, or it may be other way around. Okay, but since I have an edge from u to v, which saying that okay, if this is a cross edge from u to v, okay, then I can say that okay, v is surely discovered before u's exploration. This v must have been discovered first. Okay, fine, because that's why I must have discovered this one first, and then I must have gone to its descendants and so on and get this one done. So this was finished, and then I went back up, and from there I went to u, and from u I saw that okay, v is already done. So there is an edge from u to v which is a cross edge. Okay, so in that case v must have been discovered first. So this relation among these two, this relation must have been true, which means that fb must be less than fu. Okay, that's what we wanted to prove, right? So we have shown that, which proves our claim. So the topological sort G lists the nodes of G from highest to lowest finish times. So as from the claim we just show that for every edge uv of G, finish time of fv is less than finish time of u. For every edge uv from u to v in topological sort order, finish time of u, this guy must have finished later than fv. Okay, fine. So fu is greater than fv. So u will be before v in the algorithms list. So u will come first. It must have been in the front. Okay, fine. And that's why I will get this ordering. Okay, so hence our claim that this does gives us a topological sort. Okay, so I hope it is clear the application of depth first search, how we can do a topological sort on a graph which represents dependencies between certain things, okay, which are represented as nodes, and the dependencies are represented as directed edges. Okay, so I hope it is clear what is topological sort and the algorithm for it. Thank you.